So now we'll discuss what conclusions we draw from this complex numbers and what are the basic properties of complex numbers. Okay. So as we know, the complex number can be written as x plus iota y. Okay. And when we try to locate this complex number on the complex plane, the real part will be the x coordinate and the imaginary part will be the y coordinate. So this is my complex number z. If I discuss about the conjugate of z, so in the case of conjugate of z, the real part will remain the same, but the imaginary part will be the negative of the imaginary part of the complex number. So in case of complex number, the conjugate of the complex number, it will be shifted to x comma minus y. So z conjugate will lie over here, x comma minus 1. If I see the negative of the complex number, which is minus z, this will be nothing but minus x minus y. Okay, so the complex number will come over here. And if we see the minus of conjugate of z, this will come over here. Okay, so this point will be minus x minus y, and this point will be minus x comma plus y. So minus of z is equal to minus x minus iota y, minus of conjugate of z will be equal to minus x plus iota y. Now we can easily see that the distance of all these complex numbers from the origin will be equal, and that will be equal to under root x square plus y square. Because in the distance formula, this minus sign will make no difference. Okay, the distance will remain same. So we can draw our conclusion from here that modulus of, so this will be the first property, that modulus of z is equal to modulus of negative of z, and this is equal to modulus of conjugate of z. Okay, so the modulus of complex number and its conjugate are both equal, and this is equal to, so from this complex number we derive 4 new complex numbers. This is the negative of the complex number, conjugate, and the negative of the conjugate of the complex number. Okay, and we can see that the modulus of all the 4 complex numbers is nothing but same. Okay, so let's see the next property. So let's see what will happen if I multiply a complex number with its conjugate. If I multiply a complex number with its conjugate, so let's solve this by algebraic operations. This will become x square plus 2 iota xy minus iota xy plus y square. So this value comes out to be x square plus y square. Okay, and this is nothing but the square of the distance of the complex number from the origin. Okay, which is nothing but the square of the modulus of complex number. So we can say that if I multiply the complex number with its conjugate, we get the square of the complex number. So z bar is nothing but mod z whole square. Okay, this is a very important property. Next thing, if I have 2 complex numbers and I multiply these 2 complex numbers, okay, what will happen to the argument? I have to see what will happen to the argument if I multiply 2 complex numbers. Let's say the argument of this will be theta 1 and this is theta 2. So the complex number z1 can be written as r1 e to the power iota theta 1 using the Euler form, and the complex number z2 can be written as r2 e to the power iota theta 2. So if I multiply these 2 complex numbers, their arguments will get added. Okay, this is following the same properties of logarithm. If I multiply 2 complex numbers, the arguments will get added. Argument z1 plus argument z2 plus 2k pi. So we'll study the application of this 2k pi. What is the use of 2k pi? After some time, I'll tell you. Similarly, if I divide 2 complex numbers, the argument will be subtracted. Argument z1 minus argument z2 plus 2k pi. Okay. Now as we know that the argument of a complex number will always lie from minus pi to plus pi. Okay. So let's say the argument of this complex number is, let's say 3 pi by 4, and the argument of this complex number will be pi by 2. So what is the argument of the complex number which we obtain from multiplying these two complex numbers? The arguments will get added. Okay. So the resulting argument will come out to be 5 pi by 4. But since we know that the argument of a complex number always lies between minus pi to plus pi, I have to get this argument between minus pi to plus pi. So what will I do? I'll add a suitable integral of 2 pi, okay, such that this argument will come in this category. Okay. So how can I do that? If I add minus 2 pi over here, okay, if I added plus 2 pi, this will get out of this domain. Okay. If I add minus 2 pi, this will become minus 3 pi by 4. Now this argument lies between minus pi to pi. Okay. So this is the application of adding these 2k pi over here. Similarly, if we have the argument of first complex number as 3 pi by 4 and the argument of second complex number minus 3 pi by 4. Okay. So what will happen if we divide these two complex numbers? The net argument is coming out to be 3 pi by 2. But the argument of a complex number can never lie out of this interval. Therefore, to convert it into this interval, I will add minus 2 pi. Okay. So that this will become minus pi by 2. So this is the application of adding this 2k pi over here. Okay. Now let's see what happens if we see z to the power n. Okay. So I know this complex number 1 plus iota. What I did, I took a cube of this complex number. Okay. Instead of solving the whole formula, okay, by completing the formula of a plus b whole cube, what I can simply do is convert it into Euler form and then see what happens. Okay. In the Euler form, this can easily be written as root 2 e to the power iota pi by 4. Now if I cube this complex number in this way, we will reduce our calculation to a very big extent. So this will become 2 root 2 e to the power iota 3 pi by 4. So by cubing this complex number, we get a complex number whose modulus is equal to 2 root 2 and whose argument is equal to 3 pi by 4. So this complex number is nothing but 2 root 2 cos 3 pi by 4 plus iota sin 3 pi by 4. So we can easily see that if I took a cube of this complex number, the argument gets multiplied by 3. Okay. If I took a cube of this complex number, the argument gets multiplied by 3. So if I took a power n of this complex numbers, what will happen to the argument is that the argument will get multiplied by n. So we can say that argument of z to the power n, this is nothing but n times the argument of z. This is a very important property. And what will happen if I take the modulus of this complex number, that this will be equal to modulus of the complex number z to the power n. Okay. So instead of opening the whole complex number in the algebraic form, we can easily apply the Euler form and get these two results. Okay. So now let's see another application. Another property is if the complex number is purely real. What happens if the complex number we know is purely real? If we know that if the complex number is purely real, like x plus iota y is purely real, we know that there will be no imaginary part over here. So we can say that the complex number will be equal to its conjugate, because there is no imaginary part, x minus iota y. This plus iota y or this minus iota y will make no difference. So we can say that if the complex number is purely real, z is equal to z conjugate, because there will be no imaginary part and that will make no difference. Okay. And if the complex number is purely imaginary, in that case we only have the imaginary part. Okay, in this is z and this is conjugate of z. We only have the imaginary parts, so we can easily say that z is equal to minus of z conjugate.